This is just too. uh, Professor Suskind, I love you. This is like the test of just.
How many people here know what EPR stands for?
Clearly, everybody who is looking at this should know and be raising their hand, right? I'm just going to take a guess and just say Einstein, Podolsky, Rosen.
A good fraction of you. Good. It stands, of course, for Einstein, Podolsky, and Rosen, but it also is the phenomena of entanglement, quantum entanglement. Now, I'm not going to tell you exactly what the quantum entanglement is. It's what Einstein called spooky action at a distance. I'm just going to tell you a very, very simple version of it. Two things, they could just be two electrons, or they could be two nuclei, or they could be two macroscopic objects, are entangled if, by measuring one of them, you find out certain kinds of quantum information about the other one, no matter how far away that other one is. Let's just call that entanglement. Now, all my physicist friends know that I'm being oversimplified, but there is this phenomena of sharing information between two different distant systems that's called EPR entanglement, and it's a very mysterious phenomenon. And I'm not going to explain it now, we'll just say it exists. That was the year 1935 when Einstein, Podolsky, and Rosen discovered, or at least, let's make it simple, discovered entanglement. It was incidentally a very good year for Einstein. Einstein, I think, had three really good years. 1905, when he discovered all of modern physics, except for gravity, except for the rules of gravity. 1915 or so, when he completed the general theory of relativity and understood gravity. And 1935, which is much less famous, in which he discovered this phenomena of entanglement, but the same exact year, he discovered something else called Einstein-Rosen bridges. Einstein, or sometimes called wormholes. Wormholes are a solution of Einstein's equations in which you have two black holes far away from each other with a kind of tunnel of space between them. You can't see that tunnel of space. It's in some interior space that can't be seen, but the two very distant objects are connected by I call it a tunnel, I call it a bridge, I call it a wormhole, all the same idea.
Einstein Rosen.
You've seen these things in science fiction, people jumping into wormholes and so forth. I always thought it was nonsense, but not completely. What's the idea? If you could go as fast, what it sounds like is you can jump into one black hole over here and pop out.
What it sounds like is I need to get to Berkeley.
Over here. Well, we'll see that you can't do that, but nevertheless, that's what a wormhole resembles. The science fiction idea of a bridge between very distant places. Now, what does ER, that's the bridge, Einstein-Rosen bridge, have to do with EPR, other than they have two letters in common? Nothing before 2013. Nobody, and I'm absolutely convinced that Einstein was among that nobody, had any idea that entanglement and wormholes or Einstein-Rosen bridges had anything to do with each other. And after 2013, they had everything to do with each other. In fact, the idea goes with the acronym ER equals EPR. You could call it P equals 1, but nobody does. ER, the idea of a bridge between distant regions of space, and the idea of entanglement are the same idea. So I'm going to show you a little bit about how that works.
Just like. now.
The rectangle here is supposed to be space, a big region of space. Over here on Earth, we have a bunch of particles. Far away on Alpha Centauri, we have another bunch of particles, two clouds of particles. Those particles have never been in contact with each other. They don't know about each other. They're completely separate with no prior interaction between them. I'm going to take this sheet of space and fold it over, not because it's folded over, but just I want to draw it that way to make a point. But it is still true that this cloud over here is far from this cloud because you have to go around this long way to get there. What happens if you let those clouds of particles collapse, shrink? They form black holes. That's what a black hole is. It's the shrinkage and collapse of a star, for example. These could form a star eventually, and after a star, they could form black holes. And those black holes will be completely separate from each other with no connection between them. On the other hand, let's do something else now. Let's take a bunch of entangled electrons, or a bunch of entangled particles. Half of them are over here, and half of them are over here. Now, how do you create, well, the green line here just indicates that this particle is entangled with this one, this particle is entangled with this one, no, not that one, this one. How do you create such a situation? To create it, you have to create the entangled particles near each other. You can't create entangled particles far from each other. You have to bring the particles together, you've got to let them interact with each other, and they will become entangled. But once they're entangled, you can take the half of them that's down here, separate it, well, let's say we take this half of them and bring them all around here so that we wind up with two clouds of entangled particles. Now we let gravity do its work. And when gravity does its work, again, it creates two black holes, but the black holes are now connected by an Einstein-Rosen bridge. In other words, entanglement and wormholes are in some sense the same thing. Two black holes which are entangled will necessarily have a bridge between them. Two black holes which are unentangled will not. This is what's called ER equals EPR, and it was a major discovery. It seemed ludicrous at first, but it very quickly caught on. Is now part of the standard law. What can you do with it? Okay, so let's imagine now that we do have such a wormhole connecting two very distant black holes. One of them, Franklin has control over. Control means he can do things to it, he can jump into it if he wants. The other one, Linus, has control over. And they're very far away. One is on Alpha Centauri, the other is on Earth, but they have this Einstein-Rosen bridge connecting them. Well, with enough care and enough fine-tuning, they can arrange these black holes so that they can each jump into their own black hole and in a very short period of time can meet at the center and shake hands. What they cannot do, at least without some further considerations, which I'll come to, or if I have time, I may not have time, Linus cannot jump into one, pass through, and come out the other one. That can't happen. Now, the fact that it can't happen is time, I may not have time. Linus cannot jump into one, pass through, and come out the other one. That can't happen. Now, the fact that it can't happen is both known from a quantum mechanical point of view. It's called the no-signaling theorem for entanglement. And for wormholes, it's called the non-traversability of wormholes, the impossibility of traversing through them. And it turns out those are the same phenomena. One quantum mechanical, the other gravitational. Now let's come back to A equals RB. The encyclopedia A in black hole number 1, or left-hand black hole here, is encoded in the radiation in region 2 over here. Our problem before was that sounded crazy, somebody manipulating the radiation over here could perturb what's inside the black hole in just such a way that somebody who jumped into this black hole over here would detect that a very, very distant observer had done something to this group of photons over here. That sounded outlandish. But now we know that if these photons over here are entangled with the black hole, which they will be, that an Einstein-Rosen bridge, and from outside you can't see that Einstein-Rosen bridge, but the Einstein-Rosen bridge will open up. And so anything anybody does over here will affect what's behind the horizon of the original black hole. In other words, A equals RB makes perfect sense. Again, it has to do with this basic idea that information is not where you think it is. This is a radical example of it. What about the wormhole side of it? How can it be, why should it be, that somebody who goes into one black hole in Alpha Centauri can't get through the wormhole and come out? Well, one end of the wormhole is in New York, the other end is in California. Think of it as a tunnel between the two places. Why can't you drive through that tunnel? And the reason is that Einstein-Rosen bridges, and this is a gravitational phenomena, tend to stretch and expand with time. That's the solution of Einstein's equations, gravitational equations. Wormholes grow. So, who was it, Franklin? I can't remember, Franklin or Linus. If Linus tries to drive into the New York side, he will encounter the fact that the wormhole is growing. And in fact, it will grow so fast that he cannot outrun the growth of the wormhole and will simply never get through to the other side and come out the other side. That's the non-traversability of wormholes. You can't even send a light signal through, because even a light signal will not go fast enough to outrun the growth of the wormhole. That's the gravitational side of it. Is there a quantum side of it? Yes, there is, and I don't have time to tell you what it is. I will tell you what it is. That's the gravitational side of it. Is there a quantum side of it? Yes, there is, and I don't have time to tell you what it is. I will tell you what it is. I don't have time to explain it, but I'll tell you that it's a computer science concept. It's called the growth of complexity. The black hole, quantum state of the system is becoming more and more complex. It's very much like this information scrambling that we talked about, having to do with falling. The quantum state of the wormhole evolves, it becomes more and more complex, and that complexity translates into the growth of the wormhole. So these are all these very, very remarkable correspondences, which tend to make us think that not just that there are deep connections between quantum mechanics and gravity, but it's at some level, as I said, I'll say it again, they're two sides of the same coin. Okay, so we have the idea of a quantum hologram encoding information, which could be far from where the object that it's encoding is. And what is the other side of the coin? The other side of the coin is gravity. I like this picture. It's my favorite one of all. Whoops. Side of the coin, the other side of the coin is gravity. I like this picture. It's my favorite one of all. Whoops. What happened here? Oh my. This is a totally different subject. Let's see. Gravity. I like this picture. It's my favorite one of all. Whoops. What happened here? Oh my. This is a totally different subject. Let's see if we can get it back. It's my favorite one of all. Whoops. What happened here? Oh my. Is it?
Early growth and correlation function.
totally different subject. Let's see if we can get it back. I like this picture. It's my favorite one of all. Whoops. What happened here? Oh my. This is a totally different subject. Let's see if we can get it back. Oppenheimer lecture. Good. Here we are. All right, now let me address. Let's see, how much time do I have, Raphael? Am I running out of time? $15 seconds? Oh, 15 minutes. I don't need 15 minutes. We'll have lots of time for questions. Okay. There are criticisms. Oh, incidentally, one might point out that most of these ideas grew not just out of the combination of quantum mechanics and gravity, but string theory. How string theory got into it, I haven't really said very much about. But let me tell you that all of the precise examples, all the mathematically precise examples of this correspondence tend to come from systems which were invented or discovered in string theory. Of string theory, quantum gravity has been the victim of an enormous amount of criticism. The criticism, which first of all, I think is unjustified, but what does it have to do with? The criticism, I would say, stems from the fact, and I think it is a fact, that good science almost always spreads its influence far and wide into many fields of not just physics, but even outside of physics, and in particular into engineering, into technology. And that's a pattern that we've seen over and over and over again. Special relativity led to nuclear energy. General relativity, we use it for navigation by satellite, believe it or not. Quantum mechanics, the list of technological advances. And quantum mechanics was not invented by people trying to do technology. It was invented by people who were curious about the atom. Quantum mechanics, among other things, it led to the MRI machine. But so many things that I have that the list would go on and on. Quantum electrodynamics, trying to understand the quantum mechanics of electrons and photons, in particular photons, led to the laser, or at least is closely connected with the laser, and so forth and so on. What about quantum gravity, general relativity, and its connection to quantum mechanics? It seems so infinitely remote, with no connections or applications to the rest of science. It could be that that's true. It could be we're just stuck with that. But that has not been what is happening. First of all, these connections between quantum mechanics and gravity have led to new insights into strictly phenomena which seem to have nothing to do with gravitation. For example, the surface of a black hole, the horizon of a black hole, behaves as if it were made of a fluid. That's something that general relativists discovered a long time, but not just a fluid, but a quantum fluid, whatever that means. One can use the fact, by knowing enough about black hole physics and knowing enough about general relativity, you can compute properties of fluids that were too hard to compute otherwise. Here's one example of something that was inspired by the connection between fluid mechanics, black holes, and quantum mechanics. It's a bound on the viscosity of fluids. Now, that doesn't seem to have anything to do with either of those subjects. Well, it's a little bit quantum mechanical. It is quantum mechanical. Eta is the viscosity of a fluid, the stickiness of it. S on the right-hand side is the entropy per unit volume of the fluid, the heat per unit volume. What was discovered in the context, not discovered by people doing fluid dynamics, people comparing properties of quantum mechanical black hole horizons with fluids, is that the viscosity is always greater than equal to some number that includes h bar, that includes the quantum constant, times the entropy density. Will that have impact into fluid dynamics and into, probably. There are things called strange metals. Strange metals are a form of matter that was discovered by condensed matter physicists. Are they important in technology? I don't really know, but they were discovered about 30 years ago, and they were metallic systems which behaved just differently than ordinary metals. It's turning out that those strange metals are mathematically identical to certain special kinds of black holes called extremal black holes or near extremal black holes. Both sides are quantum mechanical. One side is also gravitational, extremal black holes. The other side is the pure quantum mechanics of certain materials. Information scrambling, the thing which I told you accounts for the falling of the apple as it accelerates in the gravitational field. Information scrambling is an important thing in quantum computer science. The information scrambling from black holes led to a bound. Again, another bound, but a certain constant called the Lyapunov exponent in information scrambling is always less than some other constant. To a bound. Again, another bound, that a certain constant called the Lyapunov exponent in information scrambling is always less than some other constant. That now is considered a reliable fundamental bound on how fast information can spread through a quantum mechanical system. I told you that Linus cannot get through the wormhole. Well, I was a little bit too pessimistic. With a little bit of help from something called the exchange of classical information, these little purple dots being sent from one side to the other, that's just ordinary Morse code, for example, but has no information about Linus or about anything else inside the wormhole, with a little bit of help from a little bit of classical information, you can slow down that growth of the wormhole. You can slow it down enough so that indeed Linus can get through it. That phenomenon, which was discovered in the context of gravity and quantum gravity, has led to a new protocol and new experiments for quantum teleportation. Quantum teleportation is a real thing. You can teleport information. What it means, you can't exceed the speed of light, but you can send information in a way that is completely hidden, 100% hidden, cannot be decoded by an eavesdropper. And so it's led to new protocols for quantum teleportation. Experiments are now being done to confirm that this can happen, not in black holes, but in quantum computers. I'm not allowed to tell you that the experiments are successful because I promised not to mention that they're being done and that they're working out successfully. So I won't. Quantum complexity theory, the growth of wormholes, the whole idea of gravitation being controlled by the growth of complexity has led to many new insights into how complexity of quantum systems evolve. We've seen advances coming from gravity in error correction. Error correction is the big hang-up in trying to build a quantum computer. It's too easy to make errors in a quantum computer. You have to error correct for them, and a whole new insight into error correction has come from thinking about gravitational systems again. And finally, in the hands of one of my favorite physicists, Juan Malvicena, much of what we're talking about has had a very interesting influence in cosmology, in inflationary cosmology. So far from being a totally isolated thing outside the framework of any other science, this quantum gravity is beginning to have an effect, which, let's just put it this way, condensed matter physicists and quantum computer physicists and theoretical cosmologists are being forced to learn what ADS-CFT means. And they are learning it. They're learning it and using it. Cosmologists are being forced to learn what ADS-CFT means. And they are learning it. They're learning it and using it. So this is exciting. This is cosmologists are being forced to learn what ADS-CFT means.
Quantum.
And they are learning it. They're learning it and using it. So this is exciting. This is a very, very exciting period in the development of physics. It is also one which is very, very difficult to explain to a general audience. You know, when you give a lecture like this, well, what did Lincoln say? You can please half of the people, half of the blah, 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 of the time. Well, you can please half of the audience, half of the time, and so forth and so on. I think the real truth is, in a lecture like this, you're lucky if you can satisfy any piece of the audience even a little bit, because the ideas are complicated, they're difficult, and so forth. you do your best. You do your best to try to explain, and I've tried to explain as well as I can. I hope you have gotten something out of it. I hope there's at least one person who has gotten something out of this lecture. And I thank you for listening.
Okay, we have some time for a few questions.
As I can. I hope you have gotten something out of it. I hope there's at least one person who has gotten something out of this lecture. And I thank you for listening.
Okay, I'll speak up.
It may be necessary to, oh, okay, try it.
Okay, how are you? There's an experiment going on using drones to detect quantum waves. Drones. Drones. The stuff flying around in Ukraine.
Bombs? Drones.
Drones. Yeah.
Particles collapse, shrink. They form black holes. As I said, I could say a lot more, but it would take... Between the what? Yeah, absolutely. Yeah. For example, you have these two entangled black holes which form the wormhole.
Experiment going on using drones to detect quantum waves. Drones. Drones. The stuff flying around in Ukraine.
Bombs? Drones.
Drones. Yes. And you're planning on there's experiments going on using these to detect quantum waves. How are they? Okay, I guess it's an interesting.
I have no idea.
I'm interested in the drones. So okay, that's. I'm sorry.
Tell me. Well, I never heard of that. Maybe.
Okay, we have a question.
Hi, hello. Just out of curiosity, did you draw the Charlie Brown drawings yourself, or did you
I'm
find
having a little
this?
difficulty hearing. Can somebody closer?
Did you draw the cartoons yourself?
Can I draw the...
The cartoons. Did you draw those cartoons? The Peanuts cartoons. Did you draw them yourself?
Oh, yeah.
Yeah.
Some of them I just copied, but they were all hand drawn by me. Yes. My first ambition had been to be a painter, not a house painter, a picture painter. The problem was I had no talent, whatever, or at least my talent was maybe being able to draw Charles Schulz cartoons, but I really wanted to be Picasso. Didn't work out.
I have a couple of questions from online. How can a wormhole grow faster than the speed of light?
Well, locally, each piece of it is growing. The rule is not that one thing can't exceed the speed of light. It's one thing cannot pass another close by at faster than the speed of light. The universe, for example, in some sense grows faster than the speed of light. The accelerated expansion of the universe tells you that if you're far enough away, just the Hubble law, that things will be moving away from you faster than the speed of light. But it does tell you that you can't get information from that far away. And that's what creates a horizon. It creates a cosmic horizon. The same is true here. The wormhole can grow, but if it's growing that fast, you can't get through it, for one thing, and you can't receive signals from far away along the wormhole unless this idea of classical information being sent back and forth can come and slow the growth of the wormhole. And that is something that there's mathematics for it. And in some way, it's being tested in the laboratory, not in real wormholes, but in entangled quantum computers.
Thanks for the talk. So if the information in everything is really all scrambled up and delocalized, why does it act in any way that makes sense to us? Why is physics local to us?
That is a really good question. Now, if you just take some random quantum system.
Thanks for the talk. So if the information in everything is really all scrambled up and delocalized, why does it act in any way that makes sense to us? Why is physics local to us?
That is a really good question. Now, if you just take some random quantum system, it will have some features that look somewhat gravitational in character, but it will not have the degree of locality that we expect in the real world. It's only very, very special quantum systems, very, very special candidates for the holographic screen, let's say, which show the kind of locality which you're asking about, Those special quantum systems are generally gauge theories, whatever, if you don't know what that means, that's okay. And they're also very, very strongly coupled, very difficult systems to analyze. So you're pointing at one of the most important questions to understand what the nature of the very, very special systems that behave with this kind of ultra locality that the real world seems to have. And that's as far as I can go with it, because I think the answers are yet to be given.
First of all, fantastic lecture. It was great, but I'm not going to state that I understood.
No, of course.
Right. But so one of the person who happens to have worked on strange metals and thought a little bit about quantum computing, how much of the connections between the quantum gravity and everything you've been saying and these other fields which some of us work on is because of the mathematics discovered in the process of working out theories, string theory and working out theories, and how much is some deeper connection between the phenomena?
Okay, I think the connections are deeper. Certainly that's part of it. Just the mathematics seems entirely similar. You probably know about the Sachdev-Kitaev theory. That's an example. Yeah, but a lot of the physical phenomena, certainly that's part of it. Just the mathematics seems entirely similar. You probably know about the Sachdev-Kitaev theory. That's an example. Yeah, but a lot of the physical phenomena experienced in that system are identical to the physical phenomena that you would expect in a near-extremal black hole. So I'm hesitant to say that it's just the mathematics. I don't think there is. I think there is a real physical similarity, if that's what you're asking. I think there is. Yeah, we'd have to sit down and talk about that, obviously. But
I have another question from online, if I may.
Uh-huh.
Yeah. So, can you say a few more words about the growth of quantum complexity and how it corresponds to the non-traversability
so
of
many words you
wormholes?
wouldn't believe it, and I have. But I'm not sure this is the venue for it. Quantum complexity. Well, I'll tell you what quantum complexity is. First of all, let me tell you what complexity is. Complexity means lots of different things to different people. You might think, for example, a beautifully designed building or something, or a beautifully designed car is complex. No, it's less complex than almost anything you can think about in that sense. Complexity is just, in other words, I have a very complex relation with my mother-in-law. Fortunately, I had a very good relation with my mother-in-law, but you could use the term that way. In fact, a very special thing is meant. Complexity, if you have a given problem, complexity is a measure of the shortest number of steps to solve that problem. Let me give you an example. Theorem proving. You start with a bunch of axioms, and now you have some theorem that you think might be a theorem. And so you go to try to prove it, and you prove it. Okay, it took you a certain number of steps. That number of steps might not be the cheapest and least number of steps that it takes you to prove the theorem. What do I mean by steps? Steps are the use of the logical axioms together with the rules of logic, each one being used once as a step. Your proof might involve 550 steps. The complexity of a theorem is a measure of the least possible number of steps that it would have taken to prove the theorem. Another example from quantum mechanics or quantum computation is you have a quantum computer that it would have taken to prove the theorem. Another example from quantum mechanics, each one being used once as a step, your proof might involve 550 steps. The complexity of a theorem is a measure of the least possible number of steps that it would have taken to prove the theorem. Another example from quantum mechanics or quantum computation is you have a quantum computer and you're going to put into it some simple state, and you want to run that computer and get to another state which may have some interesting information in it. Okay, quantum state of a bunch of qubits or something like that. You can think of different ways of getting there. There are different routes, different series of gates, different series of processes that could bring you to that target state. The complexity of the state is a measure of the fewest number of simple operations that can get you there. That's the notion of complexity. Now, that's exactly the notion that's used in this wormhole situation. The wormhole grows, which is simply another way of, which means that the quantum state of the two black holes evolves with time. It's a general feature that complexity increases with time. In other words, you go to states which are harder and harder to get to, which would take more and more steps to get to them. And curiously, interestingly, there appears to be a connection between how complex the quantum state of the black holes is and how big the wormhole is. That seems to be something that's fairly well confirmed by now. And so it is believed that the growth of the interior of the wormhole is equivalent, that's the gravitational side, that's the general relativity side, equal to the tendency for quantum complexity to increase with time for a complex, for a chaotic quantum system. So I'll have to leave it at that because growth of the interior of the wormhole is equivalent, that's the gravitational side, that's the general relativity side, equal to the tendency for quantum complexity to increase with time for a complex, for a chaotic quantum system. So I'll have to leave it at that because, as I said, I could say a lot more, but it would take more time than we can expend.
That was great.
Hello. So I was wondering, since you said that the center of a black hole, or at least the holographic surface of the center of a black hole, acts like a fluid, uh, would solving
The horizon, which is a kind of holographic surface, yes.
Okay, so if it acts like a fluid, would solving the Navier-Stokes equation be a step forward to figuring out what happens at the center of a black
Well,
hole?
I rather think, frankly, I think it will happen the other way. That people will be able to solve the gravitational equations for this fluid and make steps that direct attack on the Navier-Stokes equations would be too hard for. So my guess is it will happen the other way, that not solving the Navier-Stokes equation won't teach you that much about black holes, because I think it's just too hard to do. But solving black hole equations, which are a lot easier because they're just Einstein's equations, might very well teach us a lot about dynamics of fluids. That would be my best guess as to which way the information will flow there. But there are other experts on that subject here, and I think you're an expert, right? Yeah. Yeah, Yazunori. Yeah. Well, I don't know who somebody's in it.
Oh, I had a question here. I don't know if he knows it. Anyways,
Information will flow there. But there are other experts on that subject here, and I think you're an expert, right? Yeah, Yazunori. Yeah. Well, I don't know who somebody's in it.
oh, I had a question here. I don't know if he knows it. Anyways, I was wondering if there is a relationship between the surface and the entropy.
Between the what?
Oh, it's here. Hello.
Oh,
I was wondering if so you mentioned there is a bound on the viscosity of the black hole and the entropy. So since the viscosity somehow seems to be on the surface of the black hole, is there a relationship between the surface of the black hole and the entropy? And if so, why?
black holes and horizons have entropy. They have a uniform entropy distributed over the horizon. They also have viscosity. So it was realized by, I think he was a condensed matter physicist, Son, S-O-N, that no matter what he tried to do to the black hole, he could never get the viscosity of the surface fluid to be less than a certain amount, which was proportional to the entropy. And to be less than a certain amount, which was proportional to the entropy. And that was a pure black hole study. And it turned out that when people looked at experiments on the least viscous fluids, no matter how they manipulated the fluids experimentally, nobody found a fluid that exceeded the bound. It was Son and Staronets who discovered this bound. I just took that as an example There's nothing particularly special. There are lots and lots of examples like this. This one was easy to explain. There's a nice simple equation that goes with it, and it's so down to earth that it's very easy to understand. Not understand where. It comes from, why it's true, but what it says.
Sir, okay. I have two questions. The first one is, I'm not very familiar with this quantum gravity before this lecture. And there's one thing that seems very weird to me is that, where is the quantum holograph? And does it physically exist? And this is a...
You're asking where the quantum...
Yeah.
I think the answer is that you take any region, whatever, this region here of space, and you want to, the room, and you want to ask how the information is encoded, and the answer is that the amount of information you need to describe the interior of this room is never more than the surface area of the boundary of the room. And so you can always say, you pick your region, and is that the amount of information you need to describe the interior of this room is never more than the surface area of the boundary of the room. And so you can always say, you pick your region, and then the answer will be on the boundary of that region. So it's a mathematical statement. What about the universe? Well, the universe does have a horizon. The natural place for the hologram describing the entire universe would be at the horizon of at the cosmic horizon of the universe. But that's something that is still being studied. So the natural thing to say is we take the whole entire observable universe. It's bounded by something called the cosmic horizon, and that would be the natural place where you might want to say the hologram was. Now, I'm not sure that all my colleagues agree with that, and that's still something that I think is work in progress.
Okay, and the second one is really quick and is related to a former question. How do you define 2 points are nearby? As we discussed that you cannot travel greater than at a speed greater than the speed of light between two nearby points, and to what extent does these 2 points can be considered as nearby, as you stated?
You can send messages back and forth in a small amount of time. You'll say they're nearby. I'm not sure what else to say.
As you stated.
You can send messages back and forth in a small amount of time. You'll say they're nearby. I'm not sure what else to say. I don't know, Raphael, when do you say 2 points are nearby?
Hi, thank you for the lecture.
Good.
Oh yeah, here. So the famous quote-unquote historical dilemma is that the Copenhagen interpretation of quantum mechanics is not reversible, while the Schrödinger equation is very much time symmetric. Do you believe that these deeper insights into the workings of is that the Copenhagen interpretation of quantum mechanics is not reversible, while the Schrödinger equation is very much time symmetric? Do you believe that these deeper insights into the workings of quantum mechanics and as they relate to general relativity, as you laid out in the lecture, will deepen our understanding of our interpretation of the wave function, or even perhaps change or offer a new interpretation of the wave function?
I'm only going to say that that's a wonderful question. I think that is a really, really good question. I've always felt that the puzzles of quantum mechanics, the many worlds interpretation, all the very, very confusing things about quantum mechanics would only eventually get solved when we understand the connection with gravity. I still think that, but if I knew how to do it, how to make those connections, I would have published them. I mean, my feeling is that the answer to your question is understanding these aspects of quantum gravity will tell you more about the inner workings of quantum mechanics, but nobody has really, that's not been a primary concern of the people doing this kind of work. They tend to be very focused, pragmatic people, if you can call a theoretical physicist pragmatic, who will tend to solve problems that can be solved. This is part of the art of being a good theoretical physicist, is to identify those problems which are hard enough that the results of them, of a solution, will matter and be important, but were not so hard that we'll just sit around for 100 years scratching our butts over them. And so the general feeling of my friends and so forth, and I sort of share it, is that these problems of the foundations of quantum mechanics are real problems, but boy, they've been around a long time. People have struggled with them. People have not been able to make any real sense out of it. It's not even clear they're real. You know, what Feynman said about it, he said the problems are so confusing that he can't even tell if there's a real problem. And that is the way it feels. You know, it's like thinking about consciousness so the pragmatic side of physicists tends to make them steer away from problems like that. Will they come back to it? Perhaps. But at the present time, I think all of this has not impacted the most fundamental understanding of quantum mechanics, which is disappointing in a way.
Okay, we have time for two more questions, I think. One at the front here.
It tends to make them steer away from problems like that. Will they come back to it? Perhaps. But at the present time, I think all of this has not impacted the most fundamental understanding of quantum mechanics, which is disappointing in a way.
Okay, we have time for two more questions, I think. One at the front here.
Yes, I also have a question about, we talked before about collapsing a set of entangled particles into a wormhole at one here and one at Alpha Centauri. And I wanted to ask if that in turn also means that if we have a wormhole and it decays, that we also get back a set of entangled particles.
I am still having a little trouble hearing. Can anybody repeat it? Some voices, and it's nothing special, some voices I simply have difficulty. There's a certain range of frequencies.
Just answer.
What's that? Yeah, absolutely. Yeah. For example, you have these two entangled black holes which form the wormhole. What happens if those two black holes evaporate? They each just get transformed into radiation particles that go out, but those particles will be entangled. So that's exactly right.
One last question just here.
Yeah, last question because I'm beginning to fade.
Try now. Okay, I'll say that again. I'll ask a much simpler question than I was planning to. You mentioned that there's a definition of the Lyapunov exponent that has to do with quantum gravity. I was just wondering if you could say more about what system that exponent is referring to and where that definition comes from.
Well, it's a wide variety of systems, but any system, the most well understood case, I would say, is this SYK model, which is also a theory of strange metals. The Lyapunov exponent has to do with exponential growth. When anything grows exponentially, it varies like e to some constant times time. That constant in this context is called the Lyapunov exponent. What is it that's growing? Well, the simplest way to say it is it's the growth of the region of influence of a perturbation. In other words, this growth of what I called size earlier. What did you ask me again? I forgot. What system is it referring to? Any kind, pretty much any kind of quantum chaotic system. But as it question, because I'm beginning to fade. And it's nothing special. Some
wormhole and it decays, that we also get back a set of entangled particles.
I am still having a little trouble hearing. Can anybody repeat it?
I'll say that again. I'll ask a much simpler about.
The Lyapunov exponent has to do with exponential growth. When anything grows exponentially, it varies like e to some constant times time. That constant in this context is called the Lyapunov exponent. What is it that's growing? Well, the simplest way to say it is it's the growth of the region of influence of a perturbation. In other words, this growth of what I called size earlier. What did you ask me again? I forgot. What system is it referring to? Any kind, pretty much any kind of quantum chaotic system. But as I said, the best understood one at this point is this SYK theory of strange metals, which is also a theory of extreme or near extremal black holes. SYK, that's the initials. Sachdev, yeah, and Kitaev. So that's where most of it has been worked out in the greatest detail.
Well, Lenny, I think the only way that people would be left unsatisfied is only insofar as they're hungry for more.
Yeah.
So thanks again, Professor Susskind.
Wow.